Here we are for part number 2, part B for lecture 2 on load analysis. The purpose is to do a couple of examples. Before we start with the examples, I do want to, before we start the example number 1, I do want to go over a few things. I want to set up a few things here clear. It should be more of a review, but if it's not clear to you, then that's fine. When we do load analysis, we have to know how many section cuts I need to make. The section cuts are governed by discontinuities. They can have discontinuities in terms of loads, geometry, boundary condition, cross-section, or material. Let's take into consideration this arbitrary hypothetical beam that I just made with all these arbitrary hypothetical loads that I made. So you start here and you say, hey, I need to make one section cut here. Okay, because obviously you're starting and you want to know what your loads are there. Then when you keep on going, you say, hey, wait, I think I tapped on this one because I have a load discontinuity. That means I need to make another section cut. Then you see the load there's a boundary condition. You say, wait, I tapped on this one. So that means I need to have another section cut. Then you keep on moving. Hey, wait, I got a moment applied. That's a load boundary condition. I have to have another section cut. I keep on going and say, hey, wait, I'm going to have a cross section. The cross section is going to change here. So that means I need to have another section cut. And I keep on moving on. Now I have distributed loads. But this still counts as one load. So I have to have another section cut here. And when the load stops, then I need to have another section cut. Now, so that would mean I need to have 1, 2, 3, 4, 5, 6, 7 section cuts for this problem. Then you could do another cut right here in the corner just to make sure that everything is balanced, okay? So that check number 8 is more of a check and I strongly recommend that we always do, okay? So to understand how this really works, let's consider a few cases. The first thing I want to say is, let's suppose I have a case of free load and I only have a point load applied here. And you want to start your cut, right? So let's suppose this is part of a beam. Okay, it's a long beam. And you want to know what your load looks like right there. So the way we define this, let me go one step back. The way we define this is, if I have, let's say this is point 10, if I say 10 plus, I'm talking about the cut just after 10. Okay, that is 10 plus. If I say 10 minus, it's a section cut just before 10. So that's what those minus and pluses mean. Your book uses a different nomenclature. By the way, we are in chapter number 3 of your textbook. You can follow us there. But just kind of explain what is really going on and how to find the free body diagram. So when I do my analysis, I need to start with what my initial loads are. You have to use your positive convention. Your positive convention is NXX is positive in this direction. Let's suppose I have a load 10 applied here. Then you will do a summation in X, and that will say 0. That would tell you that NXX at X equal to 10, 0 plus 10 is going to be 0. And that would give you nxx at x equal to 0 plus is going to be minus 10. So that is just your nxx sub 0 in your equation. And you may ask, where do we use that for? Well, if you remember, and you can derive this equation, I need to use this equation. In order to use this equation, I need to have what my initial value is. So if I start at 0, right, you have to always know that this is actually kind of like 0 plus. Okay, so then this would be 0, but really this is like 0 plus. Okay, and this curly thing here that you see in this equation that you're going to see my hand notes, let's suppose p of x is equal to x cubed minus 1. Then this is the same as p of x curly equal to curly cubed minus 1. That's what you put in here. I just find it easier to have a different variable here than using the same x. Otherwise, it becomes confusing having an x and evaluating an x. But if that works for you, that's fine. You can also do that. Another case that I would like you to consider, what happens if I am doing a case in which I need to do a section cut here. I have let's put a transfer load. I have a load 100 applied here, and I start with a load 50 here, and I am saying, tell me what is my load right there. There are two ways to do this problem. First, I could make the simplest way is just to make a simple section cut with your load 10, 100, load 50. Okay, so you have to put everything in the positive convention. In the positive convention every single time. This is my positive convention Vy. So you will have minus 50 plus 100 plus, let's suppose the distance from here to here is 10. So then you have Vy at 10 plus is equal to 0. So your Vy at 10 plus is going to be minus 50, right? If you take this as 50, bring it on the other side. So that is your initial starting point in this location. Also, what if I wanted to know my loads on the other side? So I could make the other possibility I could do is I could just take and make a section cut around this, and I have a load 100, and I know this load V sub 0 at 10 plus, and this is the positive sense in the opposite direction. This is 10 minus, and so if I found this guy over here, I know this is minus 50, so I know this is minus 50. Then when you do a summation here, this is minus Vy at 10 minus plus 100 plus Vy at 10 plus is equal to 0. So now this is what I'm interested in. 10 minus, going to bring this on the other side, and that will give me 100 minus 50 will give you 50. So that is the value here, and it kind of makes sense, right? So if I did here a small section cut here, you will see that your Vy is actually equal to 50. You can show that to yourself. There are many ways to do a section cut, and that's important for you to understand. Okay, so let's move on with an example. Let's consider this case. There is a problem in which somehow, after simplifying the problem, we can come up with this. Uh, these are the dimensions. In this problem, A is equal to 25 millimeters. Your B is equal to 5 millimeters. And your L is equal to 1 meter. Just watch out with the units, otherwise you end up in trouble. So here the problem is that this is actually located here at the bottom surface, and this is your centroid. So you have to worry about this load, but this load before we start has to be pulled over. Okay, so your problem, the first thing I like to do is pull all the loads where they belong, or before doing that, just find the reaction loads. If you follow our flow chart, the first thing are reaction loads. So just as a review, how do we find the reaction loads? You're going to put your, remember, this has to be all in the positive sense. So basically, what I am saying is, remember, this is positive, right? So what will happen is, in the opposite surface, your loads go opposite. If this is going positive like this, in my negative surface, they go opposite. In this is positive, okay? But this has to be balanced. This is positive in the negative surface. And then if this is positive like this is positive like this on the other side. And the same thing, my lateral load goes like this, and so on and so forth. All the loads are opposite, and this is why I'm drawing here. So the next thing you want to do in the problem then is, you want to start doing a summation of free body diagrams and see what happens. And to do that, this is what I did. First of all, in NX, in the root, you can see that you have absolutely, let me move this. You can see that in NXXR, right, will be minus this, plus in the general sense, okay, will be PX, the whole load. I don't have any distributed load in the axial, so this is 0. So this is actually equal to 0. Okay, in my notes that I posted online as a complement, they have this. Okay, so if you just replace everything in here, you can show that NXX is 0. So I found, let me change the color of my marker. So I found that this is equal to 0. Okay, so the next step, the next thing I want to do is, I want to find my loads in my y direction. That would be transfer direction. To do that, you can see what I did here was, this is one way to do it. You can do it any other way that you learned. But I find this a lot more systematic. You might, so this is how you do this. And remember, I don't have any loads here. This is basically like if I was trying to find how much it was my B at 1 at my end point. Okay, so VYR is negative plus 0 to 1. But this is 0. This is my reaction load, is at X equal to 0 plus, don't forget that. And then, and my load, Py d psi is d of x. But here I don't have any loads. So therefore, this is equal to 0. That's why I got this 0 there. Okay, this is also another way to understand these equations. So when I do this, I find that VYR or Vy at x equal to 0 plus will be minus 100. Okay? So that's important. So the next thing I want to do is in BZ. Okay? So if you do this in BZ now, again, we are doing the same thing. I'm going to do this a little bit different than what was given here. We know that your equations are VZ at 1 is equal to minus VZR. This is the same as this is x equal to 0 plus 0 to 1 PZ this I. Okay, so so when we do this, what you realize in this particular problem is that on this particular side, you don't only have the distributed load, okay, but you also, so you can either include this on this side, but you have to know that you have to put this as a minus, but that may be confusing. So what you could do is, if that's confusing to you, what you want to do is and say, I'm going to include all the loads here plus my pond load 1000. That's actually included in the problem. Okay, that's where this comes from. And then you can say this is equal to 0, and you solve the problem and you find that VZ is equal to 1000. That's one way to do it. There are many ways to find your reactions. You just do whatever works best for you. It's a free body diagram in a three-dimensional state. Okay, that is important. So the next thing we want to do is we want to find the internal moments. To find the moments, again, we can do the same thing. If we are just using the equations, mx, you can see that mxr is in this direction. If I'm going to add this, I don't have any distributed loads here, so this will be 0. But this, it does create a reaction here, as you can see, okay? And that reaction is in the negative sense, you can see, because my positive is actually going like this, and this is creating a torque that's in this direction. And by the way, whenever you see double arrows, this means that this is the right-hand rule where your thumb is pointing in this direction. Okay, if it's going in the opposite direction, it's going inward. So that means your thumb is pointing in this direction. So if you got double arrows in this direction, that means I am doing like this, okay? And if you have double arrows pointing in this direction, that means that I'm doing my right-hand rule like this. So it depends on how you're doing your right-hand rule. That's what I mean. That's why that's negative, because when you do this, you actually are trying to rotate in this direction and making torsionist in that direction. So when you add everything up, you get this minus 25. In the same sense, I can go ahead and do, just to complete the problem, I'll let you mess around with these equations for a while. But I don't have any my. I don't have any. You don't have a distributed load in Z. In B is a constant load, so this is PL times. So this is P times L. You can see that is what's going to actually cause a moment in this direction about your VZ. So we are talking about finding this guy, okay? You don't have any distributed loads in this direction. You can see I don't have any distributed loads. Okay, so that's why you have that. The second thing you can do is you can also find what your loads look like in the other direction. And the loads in this direction actually are this. And you can see here I did put a 100 because I have a distributed load here. And this is this value, so you basically end up with this value right here. Okay, so at the end of the day, all I did was I found all my reactions. Okay, that's all I have done. And so now that we have the reaction, if you remember, let's go back. How many cuts do I need to make? In this case, this is all uniform. I just need to make one cut. I don't have any other discontinuity. Okay, so the one cut is going to look something like this. In this particular cut, I got my Vy, MXX, I got all my loads here. And then you have to be systematically disciplined to do your summations in Y, your summations in Z, and just to work your way through around that. So in this particular problem, if I was going to do that and you remember what your loads were, so let's do one, not good, Vy of X is actually equal to Vy at 0 plus, remember, minus 0x Py dxi dxi. And this is the same as we found this value. This value was, just give me a sec. That was minus 100. So this value was minus 100 minus 0x. This is 100. Dxi, if you solve for this, will give you minus 100 plus 100 times x. Okay? So that's how you find your Vy. Nx is easy because that was actually equal to 0. So your nxx of x is 0. So you have no loads in your nxx. And Vz, then if I do my Vz, this one right here, Vz of x will be Vz at 0 plus minus 0 to x Pz dxi dxi. You don't have any distributed loads you don't have any distributed loads in Vz. This is Vz right here, so you can see you don't have any distributed loads in the Z direction. So that goes to 0, and you basically end up with your initial value that's equal to 1000. Okay? So that's another way to do this problem. There are many other ways to find your moments, but this is a more systematic approach on how to do it. Let me do MYY just to show you how these equations actually work. So if you look at my notes, MYY of x is MYY at 0 minus 0x my psi minus Vz psi dxi. And what you have in the problem, this is plus, don't forget this. This gave me minus 1000, we found that. This is 0 to x, This is 0. I don't have any distributing moments. The value of this is 1000. This is this I, and that gives you 10,000x minus 10,000. Okay, that's how I found this guy over here. So if you sit down and you do this, now if you want to do it about this axis, remember everything that rotates makes anything rotate there. So in that particular case, let me just copy this here. You're going to end up, this is the equation. Don't forget there's a plus sign missing there. So you don't have any distributed loads. That would be 0. This is minus 100 minus 100 psi. Where does that come from? We found it here. By minus 100 plus 100. So that's why this goes in here. So you solve the problem. You solve the whole thing here. And this is what your loads look like. At the end of the day, it doesn't matter how you found your shear diagrams. This is what I'm expecting you to give. You have to put units to this. In this particular problem, these are all given in newtons. This is given in newtons. I believe millimeters or meters. I don't remember. I think it's millimeters. So this is what you have. No, I'm sorry. This is given in newtons meter. My apologies for that. But many times when we're going to, when you're going to plot this, many times we can non-dimensionalize this. However, let's forget about non-dimensionalization and let's learn how to run your Matlab code. Okay, so here is my Matlab code. You can all see this is a Matlab script. If you download this script, that's on D2L. If you go to D2L under Matlab files, load diagrams, you can download that. Okay, so the main script that you're downloading, you're running in Matlab, just a simple. This is how you run it, and this is the main script that you want to load. Then in this particular script, I am going to save this. Let's save this as example 1. And for sake of, I don't need to do this, you can change this to example number 1. This makes sure everything is clear, all your plots are cleared out, and you close everything if anything is open. And everything writes it to an external file called example.txt. So when you're going to start to run this, how many data points you want to run, you can put 1,000, whatever. In this particular case, I only have one dimension. I have one cut, so it goes to 0 to 1. Again, just to remind you, let me find my original problem. Original problem statement goes from 0, L, and L is equal to 1. Okay, so that's why I'm using 0 to 1. So I don't need this. You have to put it transpose, so it's actually consistent. You have to, in this particular example, I need to delete this, but this is mainly for more than multiple sections. In this case, that doesn't apply. I will give you an example with that later in a minute. So all my n-axes are 0. So this is how this is 1s, and you multiply 1 by 0. This is only one dimensional, this one cut. So in the case of Vy, let's see, what was Vy? Vy is equal to Vy is equal to minus 100 plus 100 multiplied by x. By Matlab, since x1 has to be x1, this is your dimension, you have to put a dot before that because this is a vector. Okay, before each one of these guys, you have to put a dot. Then the next thing I want to do is I also have a VZ. VZ. The VZ is constant. It is 1,000. The value is 1,000. But if I don't multiply by ones, then I'm going to get only one value. And I do want to get multiple values for this, for my entire domain. That's why I put VZ. So let's do your moments now. I'm going to do it in the same order. Let's do this one first. Torque. Mx is 25, so I can multiply minus 25.0 and delete all this. And again, I might have deleted this. You have to, Vy is equal to Vy1. Have to keep that there. I made my code general enough. Vz1, okay? So now you got Mx, you have only one component, so you leave that. And you also have one component Mz, and Mz is, so the next one is Myy, so why we just don't do Myy first? Myy, Myy, Myy1, and this is what happened here. It's easy if we just copy here, copy there, just being a little bit lazy. Myy is, you know, you don't have to do that, is minus 1,000 plus 1,000 dot multiply x1. Okay, so that's how I will get my Myy. MZZ, it looks to be more complex, but it's not that complex at all. So the way you would do this is minus 50, okay, plus 100, and you have to multiply, you have to put a dot before multiplication. 1 minus 50, you have to put the dot before the multiplication by 50. You have to put a dot before putting squared, okay, and then this will be MZZ. Okay, coming back to our code, this is 1,000 points. I define what my x will be, my nxx will be, vy will be, mxx, myy, mzz. This is the strings. This is what will be defining the x-axis and the y-axis. Okay, this is what would go in the x and y-axis. And these are basically, you may not need to mess around with anything if you did the problem as it is. This is how we plot each one of the plots. So when you plot this, what you're going to see here is a PDF file. I made a PDF file so it's easy for you to upload. And this is what the PDF file looks like. This is your NXX, your VY. I'm not sure why. Oh, I think I know what was going on here. I can fix that, not a problem. The arrows are not showing. That's because the arrows are way down here. You know, you see what your axis look like. Let me fix that for a moment. Just I thought I'd let you know, explain how I'm going to fix it. because you still have to run this, right? Um, when I'm going to fix this, I can add what I call my axis here, right? And what the axis will do is it has four values. The first value, let's start as 0. This is the value of maximum xx, so there's a maximum value in x. Now, these are the values of y. So my biggest problem was adding this. So how about we just put a 0 there? So we always start at 0, and we always go to the maximum value of x. So what you're going to see here now is I got, I think I have a parenthesis that does not go there. There you go. So now we close this. You always have to close it, otherwise it's going to give you an error. So when I'm running this, it's going to ask for selection. In this case, it's meter 3. Stresses doesn't matter, just put either one. One is good. It did give me an error. Let's go and fix it. There is, where is it? Okay, I fixed it. It was just copy paste errors. So when you open up now your plot, you see what your plot looks like. So this is what your plots look like. Now you can see the error here. And the same thing you can see for your torque. Let me explain this. Like for instance, over here, if you want the plot up here, you have to know that the value is constant, is negative. So therefore, instead of making it max, I will have to go with minimum of this to 0. And you can do help to your Matlab if you need any, you need further questions. So basically, then I will, once I'm done editing this, I run it. When I run it, I get the selections. You push meter. This doesn't matter. I just put 1. It's not calculating that anyways. I double click on this, and there you should have your shear moment diagrams that you're looking for. So this concludes example number 1.